we are very pleased to have today Franziska Weber from the University of California, Berkeley, who will talk to us on numerical methods for models of liquid crystal dynamics. Thank you, Franziska.
Thank you for the introduction, and thank you so much for inviting me. It's been nice to visit here, and also thanks for coming to my talk. And as Susan already said, I'll talk about numerical methods for liquid crystal dynamics. And I think this department is maybe not super numerical, I figured out, so I will talk more about the modeling and analysis aspect. And if I talk about something that sounds really alien to me or it doesn't make sense, please let me know, because maybe I forgot to say something important. Okay, as you can see, this is joint work with several people, and some of them are my students, Seven, Varun, and Max here. I was a friend of Max here before, but I think he's not here. Okay. All right, so yeah, let's. Oh, no. Okay, let's see. Okay, so what are liquid crystals? If you have never heard about that before, let me quickly introduce it to you. So actually, liquid crystals is like a state of matter. Like as you have a solid phase and you have a liquid phase and a gas phase, there's a liquid crystal phase that not all materials have. And materials that typically have a liquid crystal phase, their molecules have like a certain structure or symmetries. So in this case, you can picture them as like some elongated rods. But there's also like disc-like things. And because of that, they have an additional phase between the solid and the liquid phase. So you can think about the solid phase as where everything is nicely structured and ordered. And the liquid phase, it's quite chaotic, it moves around. And now the liquid crystal phase is something in between where you have some partial order. So you see the molecules more or less point in the same direction, but not exactly. And they can flow. So it's still like kind of a fluid. And we kind of abuse terminology a little bit and call these materials liquid crystals, even though it's actually a phase. And so there's different ways of how liquid crystal molecules can like orient each other with respect to each other. And that's what you can see here. And so these different types of orientations are called splay, twist, and bend for obvious reasons. And that makes them interesting. So why we're talking about this, that makes them interesting for all kinds of applications. And so one interesting property that many liquid crystal types have is that they can polarize the light. So if you take two polarizing filters and you put a liquid crystal sample in between, depending on how the molecules are oriented, the light will go through or not. And that's what you can see in this picture over here. So all these colors correspond to different orientations of the liquid crystal molecules. And I think the black part here is probably where it's in the liquid phase. So there's like some phase transition. That's why you can't see everything. Yeah, and due to that, you can use them for all kinds of applications, some of which you can see here. So many liquid crystal types, they also react to external forces like electric or magnetic fields. And that's what's used LCDs, liquid crystal displays, screens, which is what you can see here. Here, maybe you have been on a modern large airplane at some point, and you notice the window shades were gone. And so what's happening is they replaced the window shades by a smart glass, which is a glass with a liquid crystal layer in between. And so when you press the button, some voltage gets applied, and then the liquid crystal molecules orient in a different way. And depending on that, it gets dark or not. So that's what they're using. And apparently I heard they're also used in certain toilets in Japan, public toilets. So you can press the button, they're like transparent, and you press the button and it gets not transparent anymore, but I haven't seen that in person. Yeah, so this here is more experimental. This looks a little bit like maybe modern art, but it's actually bacteria immersed in a liquid crystal. And so what people try to do is to guide the bacteria with the liquid crystal. So like that maybe the bacteria would like go in the direction of how the molecules are oriented. And then so these are, remember the picture from before? The molecules have like some head-tail symmetry. These are typically nematic liquid crystals, which is what most of the talk will be about. But there's also other types where we don't have the head-tail symmetry. For example, phospholipids that you have in a cell membrane, maybe they have like a head and a long tail. So they also have this special structure. And because of that, they start like aligning in this way. So like the heads, they kind of like the water, so they go towards the plasma, and the tails, they don't like it, so they go towards each other, and that's how cell membranes form. So they are pretty important actually for us, in some sense. Okay, so here's, I already explained this more or less to you, but here's a scheme of it. So you have two polarizing filters, and then depending on how they're oriented, see here in the on state, the light goes through, then you turn off the field and the liquid crystal molecules reorient, and now the light can go through. So that's the general idea. And I'll talk about this application later on, assuming I'm not too slow and have time for it. All right, so let me talk about the mathematical models for this. So there's, I guess, two models that are most commonly used. There's more than two, but I'll just talk about these two today because I guess these are most frequently used, and I actually have worked on these. So the most intuitive one, I guess, is the Oseen-Frank director field model, developed by Oseen-Frank in 1933 and 1958. That's where the papers came out, and there's many other works. And so in this model, you have a director field, let's call it D, that is mapping to the sphere. So basically at each point in space, maybe time, you have a unit vector field that tells you where the main orientation of the molecules go. So if you think about the picture from before, here, I think it will be pointing up somehow or down because of the head here. And so then Oseen-Frank came up with elastic energy that characterizes how the molecules align. And so that's this expression here. So that's the energy density. So these three terms correspond to different alignment of the liquid crystals that I mentioned before, display, twist, and bend. So each of these terms can be kind of related to these. Don't ask me how exactly. They're physicists, and they have like this thinking of how to come up with this. And so the K1, K2, and K3 are material constants. They can depend on the temperature and also like what material you're in, and they are not necessarily the same. However, mathematicians often make simplifications, as you know, and so they set them equal to the same constant, and that's called the one constant approximation. And if you do that, after some calculation, you'll see that the Oseen-Frank energy will be of this form, which looks roughly like a Dirichlet energy, except that your D is a normal vector, so it has a constraint. But generally speaking, they may be different, and some of the math applies and some doesn't apply to the more general case. Yeah, and so then what you do is you use basically Onsager's principle. They say nature tries to minimize the energy of a state, and so if you do that, if you minimize among all vector fields with unit length constraints, you'll end up with an Euler-Lagrange equation, and so that's just a general variational principle. And so if you do this, for example, for the one constant approximation, what you'll end up with is the harmonic map to the sphere. So remember, you'd have the kind of the Dirichlet energy, and when you minimizers would solve the Poisson or Laplace equation. And so it's the same here, except you have the constraint, and the constraint results in this extra term here. So gamma is a Lagrange multiplier that enforces this constraint. And if you do some calculations, you'll see that this would be formally, assuming smooth solutions, equal to the gradient of D squared. Do you have any questions so far? So far, so good. Okay, and so, yeah, that shows you like, okay, this equation looks very simple at first, but actually this is nonlinear, and so that can cause some problems. If you look at non-equilibrium situations or the flow to the equilibrium, you can look at the heat map flow, which is going to be this equation in this case. So the heat equation with this extra constraint, just in the same way. And then I guess in nature, you want to add some more, want to make the model a little more realistic. And so what you can do is you can add inertia from the kinetic energy, or you add the fluid flow. Remember, the liquid crystals can flow, so there's an underlying fluid field. And so you would couple a system like that to the Navier-Stokes equations, or external fields like the electric field that we'll talk about more later. And so if you add all of these together, what you'll end up with is the Ericsson-Leslie equation. And that I'm not going to state here because it's just going to be a lot of equations and not helpful. Okay, so Yeah, so to show you some of the interesting properties of this model, we'll consider the model with inertia. So when you add inertia, you'll end up with a Lagrangian, and then you minimize the competition of the kinetic and elastic energy, and you'll end up with a wave equation that is constrained to the sphere. So you get a wave map equation here. And the corresponding energy will be this energy, so the kinetic energy and the elastic energy. So here I set k equal to 1. I took this one constant approximation. And formally, this is conserved by the equations. When you look at, so formally, you can see this by multiplying this by dt, and then integrating, doing some integrations by parts and chain rule. And the right-hand side will vanish because d and dt are orthogonal to each other. And you can see this by taking the derivative of the norm of d squared, which has to be 0. So formally it's preserved, but okay, you don't really know numerically. So let me show you some simulation. Sorry, that was not what I wanted to do. To the videos. All right, so here you can see the orientation of the director field at different points. I didn't plot all of them, so you'd have a lot of errors. And now, no. I need to go. Okay, let me evolve it in time. All right, so you see the arrows like flip down. So this is the director field, and then there was one in the middle that was going up for a long time, and then eventually it flipped out. So when you think about it, about the derivative of this vector field must be at some point it is not well defined anymore, right? There's some sort of blow up, and so that's what I did not prove, but conjectured that you have a blow up in the derivative of in the gradient of d, and that's what you can see here. So here, what I did is I plotted. So this is a finite difference scheme. So replace the derivatives by differences. And so I computed the differences, and then I took the maximum over the whole grid and tracked this over time. And so you see at time, so it's never going to be infinite because a finite difference, right? But as you refine the mesh, it gets larger and larger. So it looks like around time maybe 0.25, there's some sort of blow up. At the same time, this is the energy, the discrete version of the energy that's quite almost conserved. So this is for different grid sizes, and it looks like it's converging to a specific value here, and it's almost preserved. You can barely see the difference. So the scheme is that shows you that the scheme is stable, at least in some norm, but it does look like there are singularities. And actually, that's sort of a good sign, because when you look at the liquid crystals, here's another picture where you again use these polarizing filters. You see lots of these little patterns forming. And then you think about it, the director field is probably not necessarily continuous at these points. So you actually want to see that. And so this is called defects, these kind of singularities. And I guess engineers care about them because when they try to produce a material, they want to have as little as possible. It looks like they're forming quite naturally. So they want to understand this better.
Is this in 3D?
The wave map, it was in 2D, the simulation. 2D to 3D. Yeah, so the values were in the, I guess, okay, the sphere is two-dimensional, but it was like in the 2D, two-sphere. Makes sense. It's not just on a circle. Yeah. Yeah, so there's theoretical results about the wave map equation. I'm not totally up to date about the exact stages. I'm not sure if they have proved it in 2D. I think in 3D they have proved that there is ill-postness, that you can have different solutions and blah. But I think 2D is the critical dimension, so that one's really hard to actually prove the thing you see numerically. And here's another picture that I mostly picked because I thought it looked kind of cool. So you see again these patterns forming, and like when you think about orienting the vector field, it seems to be a problem. And so that's here. Yeah, here. So here you can see how to put, I guess, the So you have this color scheme, right? And then each color kind of corresponds to an angle of the vector field. And so you can see how you can kind of derive these defect patterns from that. And so they have studied this, and there's different types that they observe in the experiments. And when you look at this, some of these, they would have infinite energy in this Oseen-Frank model, because you, like for example here, because you put the orientation, you like kind of have suddenly you don't have head-tail symmetry anymore, so that doesn't make some of these continuous anymore. So there are some issues with the Oseen-Frank model, and you'd probably rather want a director field that goes to the projective plane to keep the symmetry. And even if you had that, I think some of these would have an issue. So therefore, people have thought about how to fix this or get a better model. And so one approach, oh, by the way, if these defects, if they seem kind of weird to you, you can look at your finger and you'll see similar patterns. Yeah, okay, so then they came up with other models, and one is the so-called Landau-Deschênes model that was developed mostly by Deschênes, and then there's a similar model by Ericsson, and also Weber studied these models extensively and has a nice book with derivations. So in this model, again, omega is the region which is occupied by the liquid crystal molecules, and now let's call it n because it's not exactly the same as the director field from before. So at each point you have the orientation of molecule, which is this vector n. However, now we say that n is not like a deterministic variable, it's like a random variable. And that so you have a probability density, let's call it P, on the sphere, and then behaves according to that. And let's assume the probability density is the same everywhere. And then, yeah, because it's a probability density, we'll automatically have that the integral over the sphere of P should be 1, when you take up all the events. And then since we have head-tail symmetry, we must have that P of n is equal to P of minus n. So this direction is similarly likely as this one because they're essentially the same. And due to that, we get that the first moment has to vanish. You can see that by you split up the integral into the upper hemisphere and the lower hemisphere, and then you change the integration sign n to minus n, and then they will exactly cancel out each other. So the first moment is just 0. And so the first interesting non-trivial information about the probability density must come from the second moment. And let's define the second moment like that. So we take n tensor n is just n times n transpose. Remember, n is this vector field with 2 or 3 entries, depending on what you're considering. And now n has some rather straightforward properties, such that it has unit trace. If you take the trace of m, you can take the trace inside. Now this is a unit vector, so we'll have trace 1, and so then this is again the integral over the probability density, so it has to be 1. It's also symmetric. If you take the transpose, you're taking the transpose of this symmetric matrix here. So you must get m again. And furthermore, so if you assume P is the same in every is constant, so you have the same, every direction is similarly likely, sort of like if you had a fluid or isotropic situation. Then if you make the calculation, you will obtain that m has to be the identity over a third. And so then what Deschênes did is he defined the Q-tensor as the difference of the second moment m and m0, the isotropic distribution. So basically it measures how far the second moment is from the isotropic value. And so that's basically the quantity of interest in this model. And so because of the previous, the properties of M, we'll get that Q is also symmetric in trace, and it's trace-free, because M and M0 are both symmetric, and both have trace 1, so if you subtract them, you get trace 0. And so you can write Q in this form for some eigenvectors n1 and n2. And one can also, like, if you go through the derivation, you'll see that the eigenvalues have to be between -1/3 and 2/3. And so, yeah, if you have 0, if Q is 0, that means we have like a liquid, it's isotropic. Okay, so now we need some evolution, but first, let's see if we can get any defects from this. And so here, maybe this looks a little bit like what you can see here. It looks like one of the types of defects you have seen on the previous slide. And in the Oseen-Frank model, this would have infinite energy, I think, because they're all like, right, you have a problem at the center. So you evolve this. So now it doesn't have infinite energy because you have so what you can see here is, sorry, I didn't say that. So this is the eigenvector corresponding to the larger eigenvalue. And so this is now just planar 2D. So you'd have two of them. And as you see, okay, still kind of evolving, you have this defect and it splits up into two defects that are like a different type and have lower energy. And so why is it possible? Because the eigenvalue at that point is much smaller where the defect is. So you kind of, you have the singularity, but it's sort of, I don't know, you make it weaker by making the eigenvalue smaller, or it can be zero even at that point. And yeah, so that's here you can see the evolution of the eigenvalues of the larger eigenvalue. And so we ignore the thing at the boundary, but you see initially, because of approximation, I think it would be zero right at that point, but because of approximation, it's not going to be exactly zero. Take cell averages. And so as you evolve, you see that there's two kind of holes where the eigenvalues are smaller. Okay, so, but now we need some, sorry, that wasn't what I wanted. Now we need some evolution for some dynamics, right? And so the approach is similar to before. We use one derives an energy and wants to minimize the energy and can consider the gradient flow and so on. And so the free energy is based on the considerations from Oseen-Frank, kind of a generalization to this Q-tensor framework. And in this case, the energy density looks like this. So here you have now the constants L1, L2, and L3, and they're related to the case from before, but they're not exactly the same. So like sums or differences and so on. Again, they are temperature dependent and material dependent. And now the one constant approximation would be setting L2 equal to L and the other to 0. It just happens to translate to this situation. Yeah, and so in what follows, I'll mostly consider this, but most of it applies also to this more general energy. But it's just like, it's going to be too many terms to follow, but it's just for the sake of presentation. Yeah, and then what you also need is, so remember you kind of want the eigenvalues to be in a certain range. And if you just consider this and minimize over trace-free and symmetric matrices, you will lose that. It may be anything. And so what you do is you add a bulk energy, which is some sort of double Wald potential. So if you think about it as Q being a scalar, then you can remove these traces and you'll see this is a fourth-order polynomial. And then, yeah, the constants A, B, and C, they are depending again on the material and the temperature. So then again, you can minimize this energy, Landau-Deschênes energy, and for non-equilibrium situations, you can consider the gradient flow. So this here I used to denote the variational derivative. Take the variational derivatives, and here you'll get a divergence from the gradient terms. So in the case of the one constant approximation, this term here will become the Laplacian. Yeah. So basically what you have is like sort of like a heat equation for a matrix, and then like this extra polynomial here that is projected onto trace-free objects, roughly speaking. And then, so this system has a formal energy dissipation law, which you can see if you, for example, multiply or take the Frobenius product of this equation with the time derivative of Q and then integrate, you get this term over here, you divide by n. And then here, after you integrate this one by parts, you'll see that this is sort of the variational derivative of the energy times the time derivative of the energy. So once you use chain rule, you get dEt of the energy formally. And so this is good, and we'll use this to do numerics because this will be like some sort of stability estimate for the scheme. So the goal is to replicate this in a discrete setting. Oh yeah, here's a bunch of works as you see, lots of people have worked on these different types of equations, and I think I'll not go too much into details. I'll have more time to talk about the numerics. You see, roughly speaking, the director field model was studied earlier than the Q-tensor model. And these are just the harmonic map, then the heat flow, the full system, and external fields. And so for the full system, sometimes what people do is they relax the constraint. So because it's really hard to deal with this unit length constraint numerically, what they do is they also add like some sort of double well potential and relax it, do like some sort of penalty method. Okay, so let me first talk about the numerical approximation of the gradient flow, and then a little bit about the model with the electric field, which is more realistic for applications. So this is again just the equation that I had before. Now I just wrote it in component form, and it's, as I said, a one constant approximation. And so I have to discretize time and space. I won't talk too much about space, but space is not too hard here because you just have the Laplacian, and then if you have the cross terms, yeah, it gets a little more messy, but it's not too bad. And so for the question is, how do you discretize in time then? And so what we'll do is we use this invariant energy quadratization approach that was introduced by several people here for other like gradient flow kind of like systems that had nonlinear terms. And so the idea is to introduce an auxiliary variable that is related to the nonlinear term, the bulk energy potential. Let's call this R. So R of Q here is just, this is, remember, the bulk energy density. And then yes.
For the space, are you in a periodic domain?
Oh yeah, I didn't talk much about, you can put Dirichlet boundary conditions, or you can actually also put non-zero Dirichlet boundary conditions. When you have when you have boundary conditions that depend on time, you will see this in the energy law because you're feeding in stuff or like dissipating stuff on the boundary, but you can still bound it.
But the boundary conditions are on Q, right?
Yes.
Q is the difference in the second moment.
Yes.
So what's the physical interpretation of saying Q is 0 on the boundary? So
it would be like isotropic, I guess. But yeah, you can also put it in a specific direction. Yeah.
Okay.
Yeah, so then the eigenvalues would be 0, right? And so yeah, it would be like isotropic. But you can also put something else, like something fixed that works as well. But yeah, it's a good point. I'm sorry, I should have mentioned that. Yeah, so I'm not going to talk about the boundary conditions too much because it will get harder to track everything.
Okay.
So I'll just consider the simplified case where you have 0 boundary conditions, but you can put something else. And so that actually is an important topic because like sometimes they want to like have that the liquid crystal molecules have a certain orientation along the boundary, and so they put some substrates to kind of anchor them there. And there's different types of anchoring that are like weak or strong anchoring, which strong anchoring would be Dirichlet boundary conditions. And then the weak anchoring that I haven't actually studied is when you enforce it like in a weaker way by adding a term to the energy that kind of penalizes when you go away from that boundary condition. And that should correspond to different ways of how the engineers, deal with that. Is that
okay? Yeah.
Okay, good. Thank you. Yeah. So I define this R, which is basically the bulk energy plus some constant A0. So the bulk energy could technically is bounded from below, but it could be negative. So you add this A0 to make it non-negative. So you can take the square root afterwards. But this constant doesn't matter otherwise. Then you define V of Q. That's basically this term up here. So the projection of the derivative of the bulk energy onto trace-free things. And I don't know how I ended up with a 2 here. I think it should be a 3 in 3D at least. And then P is V divided by R. And it turns out that this is exactly the variational derivative of R with respect to Q. And so now I treat R like an independent variable, and I derive an equation for R. And so I'll have an equation for Q and an equation for R. And you'll see in a moment why this is useful. Okay, so R is what this is just the definitions from before. Now you can take the derivative of R with respect to time, and you'll see that it satisfies this equation. So yeah, roughly, yeah, you can do the calculation if you want and see, and else you just believe me. And then in the evolution equation for Q, I also plug in R. So I write this bulk energy term here as R times P of Q, which is, remember P of Q is it was like V of Q divided by R, and you can compute it exactly and then get this. And so why is this useful? So now the energy law is quite easy to derive without to. So what is always a problem when you do numerics is in the continuous setting, maybe you have some nice chain rule or some product rule or whatever, and then you have to replicate this in like a discrete setting of finite differences, and often you end up with an error, like it's not exactly true. But the error is depending on higher order derivatives of the solution. And if you don't know if these derivatives exist, they could potentially blow up. So you want to you don't want these extra terms. So you want to have kind of a exact chain rule or so. And with these polynomials, they can get pretty messy and nonlinear. And so that's why we kind of do this thing. So here now, it will be very easy to do this discrete chain rule, as you'll see in a moment. So to get the energy law, you multiply this equation by R, integrate, just formally speaking, you get ddt of R squared divided by 2 here. And here you get R times PQ times dt of Q. Here you multiply by dt of Q. That gives you the dissipation. And then here you get the bulk energy, you integrate by parts, and then use chain rule. And then here this term will cancel out with this one. You don't need to do anything with it. And previously would have to use chain rule right on these polynomials. Okay, so yeah, let's now do this discretely. So delta t is the time step size, and then Tn is n times delta t, so these are the time levels in the discretization. N is an integer, and Qn of x, so we keep space continuous for now. Qn of x is hopefully an approximation of Q at Tn. Hopefully, we'll see. And then we'll derive a difference equation for Qn. And we'll need several averages, so Fn plus 1/2 is just the average of a quantity F at n plus 1 time n plus 1 and time n. So F could be Q or R divided by 2. Now this is also an approximation of F at time Tn plus 1/2, so to say, but it's explicit, so it's like an extrapolation. So you can check it's second order accurate. And then we need a time difference, so this is just the difference of time levels divided by delta t. And then, so P bar n plus 1/2 is basically plugging P into this. But because P is nonlinear, there will be different ways of doing it. So that's what I mean by it. And this is again explicit. So you want to compute the next time level, and you have n and n minus 1 given. So that's why this one's nice. This one's less nice because it's depending on your unknown. Okay, and so then the scheme is the following. So you take the difference of Q forward in time, so Qn plus 1 minus Qn is equal to your right-hand side. So when you just look at this, it looks like Crank-Nicholson's scheme. Maybe you've seen that in a numerical analysis class, how you can solve the heat equation. So this is nice to solve because this term is just linear. So you end up with some matrices that you can invert in each time step. And this term here now, the way we discretize it is also explicit. So it's also, in some sense, only depending on one in a linear way on the unknown. So R, this is the implicit average, but this is explicit. This is already given. And then for R, so I could divide by delta t, but because I have 2 time derivatives, I can multiply again. So I remove that. So R, the difference of R is given by, again, P times dt of Q. So that corresponds to this equation, roughly speaking. Okay, so why is it nice? Because it's linear in the unknown. So remember, I want to solve for Rn plus 1 and Qn plus 1, and they only appear in a linear fashion on the right-hand side. Like if I discretize, for example, this one in a different way, it would be nonlinear. I would have to use like a Newton's solver or some fixed point iteration each time step in order to get the next time step. Yeah, and the other thing that's nice is we'll see that there's a discrete version of the energy law. Okay, so I already told you it's a linear each time step. You can show that it preserves the trace-free and symmetry property of Q. You'd like that because the physical solution has that. And it's energy stable. And so to see this, you take the inner product or the Frobenius product of the first equation with the difference of Q. So that corresponds to the time derivative, right? So I'm trying to replicate the continuous proof in the discrete setting. And for the second equation, I take the average of R at n plus 1/2. So why do I take the average and not Rn? So if I take the average here, what I'm multiplying this with here is Rn plus 1 plus Rn, and then you can use binomial formula, and you'll see it's Rn plus 1 squared minus Rn squared. So this is your discrete kind of chain rule. Right? And because it's just quadratics, it's very easy to do and works out well. And that's how you get the difference of R here. So here's one discrete chain rule. This, yeah, I just told you it's just a dissipation term. But also here on the right-hand side, you can do the same. When you multiply, so here you first integrate by parts. And if it was a finite difference scheme, you would do summation by parts, but let me not go into that too much. So then you have gradient of Qn plus 1/2 times the time difference of gradient of Qn. And so again, you have this Qn or quantity at n plus 1 plus quantity at n times quantity at n plus 1 minus quantity at n. So you can again use binomial formula, and here you get the time difference of the gradient of Qn. Does it make sense? I don't know how familiar people are with this. Good, okay, cool. And then, yeah, you see these two just cancel out. I don't need to deal with them. They're exactly the same after multiplying, but the scheme is still linear. So that's why we do this business with R. Now, the problem is, of course, when you do it like, in the end, you don't know, is R still related to Q? Is R equal to R of Q? Because now you evolve with a discrete scheme in time, and it like may change, right? It may end up with some other, so something else. Yeah, and so to show, first you need to show the scheme converges. So as you set delta t to 0, you want to end up with the solution of, or a weak solution of the PDE again. So you can use the energy inequality gives you a priori estimate from which you can derive compactness. And also one can show that P is Lipschitz continuous. And then using this and the energy estimate, you get that R delta T, the piecewise constant approximation of R, is in L infinity in time and L2 in space. And Q delta T is in L infinity in time and H1 in space. And the dt of Q is in L2 in space-time. And one can also show that the difference of R has some, time difference of R has some integrability. So then for R, you can use the Banach-Arologlu theorem that tells you that up to a subsequence, you converge to some limiting function R that is in L infinity in time, L2 in space. And then for the variable Q, you can also get weak star convergence, but you want a little bit more because remember the equation is nonlinear in Q and R, so you want at least one of them to converge strongly. And for that, you use the Aubélin-Simon lemma, which maybe you have seen before. Oh, okay, I see some nodding, perfect. Okay, so you use the discrete version of that, and you get that Q delta T is converging to Q in L2. And now what you do is a so-called Laux-Mendorf argument. So you you want to show existence that the limit is a weak solution or the limit of the subsequence. So you take a smooth test function, you interpolate it with a piecewise constant, and then you integrate. And then you like sort of like integration by parts, you do summation by parts and get the derivatives on the test function. And so because the test function is smooth, all of them will converge. And then you use your weak convergence here. Here you can use the weak or the strong convergence. And then here you'll need to use the strong convergence of Q and the weak convergence of the time derivative to pass to the limit. And similarly here, use the weak convergence of R and the strong convergence of Q and the Lipschitz continuity of Q. And that's how you pass to the limit. And so in the limit, you have a weak solution of this system. And now what is left to do is you have to relate R and to Q. You have to show that R is equal to R of Q. And so what you do is you consider this equation, show that this is true, and then use that it's ODE and derive it eventually. Okay, so here's some numerical experiments. Maybe I'll skip this. And okay, you see the energy decreases. You can show the convergence rate is more or less 2 in space and time, except for R, it's a little lower in space for some reason. And let me show you the fun simulation. Okay, so Varun came up with this. He was experimenting with the scheme, and then he found this initial data that I don't know, it looks kind of fun. So that's just the initial. So this is again the eigenvector corresponding to the larger eigenvalue. And you see like it starts to align all along the same axis. And they call it a disappearing hole because it disappears. But yeah, that has no like necessary physical motivation. It's just the initial data he picked. And I showed you the defects already. So these were also done with the same scheme. Okay, so now in the last 7 minutes, I guess, let me talk about the electric field. Okay, so that was this picture. And now we need a mathematical model for that. So we already have something for Q. And now we need to find equations for the electric field and the coupling conditions. Okay, so what you can do is, let's denote E the electric field and D the displacement. And by the way, the same you could do for a magnetic field, like the equations are very similar. And the equations, or if you want magnetic and electric fields, they decouple and the treatment is the same in this particular case. Because you have, you can assume there's no free charges. And so the magnetostatics equation just become these two equations. The divergence of D is 0 and the curl of E is 0. And so if you're at least in a simply connected domain, then you can deduce that E is the gradient of a potential U, so like the applied voltage, something. And so for, then you need like, how does the liquid crystal director affect the electric field? And that's given by this constitutive relation. So here epsilon1, epsilon2, and epsilon3 are material parameters. So clearly you have a term depending on the gradient. I think that's pretty normal for any material. Then here you see how the liquid crystal director or the liquid crystal distorts the electric field. And then this is a polarization term. And so now if you combine this equation with this one and this one, you see that you get an elliptic equation for the electric potential. So you take the divergence of D, which is now given by this expression. So when you couple it, and then, okay, then you need to derive the equation for Q, which is the gradient flow from before. And now you need to add the coupling terms, and these you get by, again, doing this minimization variational principle. And then you end up with these extra coupling terms related to epsilon2 and epsilon3 term. And you see they are a little bit nonlinear. So all in all, we have this coupled system of an elliptic equation and I guess a parabolic equation. And so the energy for this, or where this comes from, is this following one. So this is again the elastic energy, the bulk energy density, and an electric energy. So these two we have already seen. I didn't write it out. This was the double well potential. And now these extra terms here come from these are the terms related to the electric field. And so you see, okay, this one looks nice, right? And this one now here, it's a little bit problematic because, so if Q is bounded, it looks good. Then you just need to derive also this one, right? You need a condition on epsilon 1, 2, and 3 to make sure that this energy is lower bounded and useful in some sense. However, it's not clear that the eigenvalue range for Q is preserved by these equations. And I've searched a long, long time and I didn't find any results about it. And maybe it's just that this equation hasn't been studied too much. So, and then we did some experiments and okay, I guess could be related to the scheme, right? You never know, is it an effect of the scheme or is it an effect of your equations? But it does look like you can produce quite large values of Q. And so that would like constrain your epsilon 2 and 1 further, and it's unclear if these are physical constraints. So I searched literature. So one thing I thought is maybe this Q here, you know, this is some sort of Taylor expansion here, right? This is like the first order term. Maybe this was a more complicated function. And I found this in other contexts with magnetic fields that they had more complicated function that was something like this. But I didn't find anything about these liquid crystals. So then I guess we thought, before we give up completely, we make a modification to deal with the system mathematically. But I'm still thinking about it. And so one thing I'm thinking would be interesting to do, to just look at the scalar version and see if you can produce a blow up for this system with the source term, which would be some sort of Cahn-Hilliard equation. But I also didn't find anything about that. So we modify the energy. So what we do, roughly speaking, is we truncate this term at R and cut it off. And so T of R, this complicated definition is just like a smoothed out version of T to make it smooth. But I think probably Lipschitz would work too. And so if you use this modified energy, then you will get slightly modified system. So here instead of Q, you have TR of Q. Also think about this equation is only elliptic if this is not too large, right? When you think about just the elliptic equation by itself. And then here, so PR of Q is the derivative of TR of Q with respect to Q. And this is a Hadamard product, so it's a component-wise multiplication. And so basically this is either 1 or 0 and or like something in between. So it gets cut off and Q is too large. So that's how you can think about it. Yeah, and then, okay, you do numerics, you have to do this discrete chain rules again, as I mentioned before. And because the electric field, oh, I don't have much time left. So the electric field, the regularity you get from the a priori estimate is that the gradient of U is in L2 in space. But you see it appears in a quadratic form here. So when you're thinking about an approximating scheme, you could even think it, don't even need to think about it numerically, it could be some other regularization. Then you need to pass to the limit somehow in these terms that are nonlinear Q. So you need to derive compactness in L2, and that you do by like using the difficult structure of the equation, like you have magnetic and electric, you have the electric field, and it satisfies this diff and the curl equation, and that you can combine in a nice way to get convergence. But this scheme is pretty nonlinear. And so one of the things that would be nice to figure out that haven't figured out yet is to make it more efficient and maybe also higher order accurate, so you don't waste as many computational resources. And okay, so one experiment, and now I finished. So one, I guess, characteristic that liquid crystals have is this so-called Frederick's transition that was first found by Fredericks and Ripieva. Not sure how to pronounce it correctly. And so basically it's a phase transition that you get when you apply sufficiently large electric or magnetic field. So the liquid crystal may be in an undistorted state before, and then basically you use the apply a sufficiently strong field to try to distort it in the field direction. And so yeah, below a certain threshold that you would like to figure out, the field is undistorted, and then as you increase it, it starts to twist until it's aligned with the field. And so what you can see here, so we did the experiment, or my student actually did the experiment, and so he increased the electric field strength. So this is just in some units that are suitable, not the actual physical units. And here's the average angle of the director field average over the domain. And you see nothing happens until about this field strength, and then they start reorienting. And I'm gonna show you this in the simulation. Okay, so the extension refers to the, so you have an applied voltage, right? So that's the boundary condition here. And then like the extension, so you have this function, you extend it to the whole domain. And so you see as you increase the value on one side, at some point they start switching. So we were happy that we could also produce this. Here's another experiment. I think here, so before it was like a gradual transition, and here I think it gets switched on at a specific time. Yeah, so right now it's 0, and then you switch on the field, and then you see the liquid crystals start reorienting slightly later. And I'm not sure why it does this circle thing. Yeah, that's something.
Are these defect formations reversible? So if you flip the external field,
Oh, good point. I'm not sure we tried that out. I would say it stays like that, but I'm not sure. Thanks for the tip. I'm not sure. I don't think we tried it out. Yeah. Okay. So yeah, that's it. Thank you. That's where I'll stop. Thank you for your attention. These are some of the references that are related to some of the things I mentioned. And we're working on, I mentioned some other things we're working on right now. Yeah. Do you have any questions?
What does SINUM stand for? It's something that I haven't seen
Science
before.
Journal of Numerical Analysis.
Okay.
Sorry.
Okay.
Question.
Yes.
In the Q-tensor equation that you showed, that the one with the numerical scheme, right before the electric field.
Okay, I need- Yeah.
Yeah, can you, I think I missed this, but can you remind me of what happens to the energy inequality? Ah, it's right there, I see. So
Yeah.
the energy
Oh.
inequality is preserved by the scheme.
In the scheme, yes, but then as you pass to the limit, you'll get an inequality.
Yeah, okay,
Yeah.
that's what I wanted to ask.
Yeah, that's a good point. Yeah.
Okay,
Yeah, because you will have to take a limit
exactly.
somewhere. Yeah, so actually, it turns out we worked on this more later on, and if you take smooth enough initial data, you get strong solutions. So you don't need to worry about this too much.
I see,
I mean,
that was what I wanted to
Yeah.
follow up.
Yeah. So you still need, I guess you still need stability, and so it's still good to like preserve this thing, but the solutions aren't that like badly behaved, at least for the gradient flow. So for the one with the electric field, I don't know, like
I see,
that system, I don't know if it has smooth solutions.
I see, but the scheme you have for that one also preserves.
So
some of the energy.
it doesn't preserve the energy. So there you'll have an energy balance, but you can bound the energy for every fixed time, like using some sort of Cronwall argument.
Right.
And so the reason is, so it's actually natural because there you do have like, when you apply the voltage, you kind of feed in or lose energy on the boundary. So yeah, you want to have that.
Okay.
Yeah.
And one quick question about the disappearing hole.
Oh yeah.
What's the intuition behind the construction of that initial condition?
I don't know, he just experimented around
Okay.
and found it. And we all thought it was
Yeah,
cool.
it's really cool, yeah.
Yeah. He was just playing around with different initial conditions, and then he found this, and we all thought, oh, it's really cool. Yeah, let's put it in the paper.
Okay.
Is that like a one-off thing? Like if you take that initial condition and change something slightly, is it just completely different?
So I think, so I'm not sure about this particular example, but there was another initial condition where it was really sensitive towards how exactly your grid or domain was. So if you like moved something slightly, you would end up with a different final state. But I think it wasn't this one. So this one here, it just goes to that. And I don't think how much we tried around, but I think this one's relatively stable. But there was some other like that we tried out. I don't think I have it on this laptop, but there was like some kind of where we had like two regions where the fields were like that and two regions like that. And then like it would dissolve, but in different ways, depending on how exactly the recurrence were. Yeah.
So it sounds very unstable.
So that one was very unstable, like I guess in the sense that the initial condition is like, it doesn't like necessarily go to the same final state. And so this initial condition, I don't think it's smooth. Like this is not too smooth. So there you would maybe not have strong solutions. Yeah. So it's like the scheme is stable in the sense that you don't have blow up. That's what I mean by stability in this sense. But yeah, I don't know if it's like, if you perturb the initial condition, I don't know if there's a result about, unless when the data is smooth, then yes, then it should like not perturb the solution too much. But when the initial condition is not smooth, then I don't know. Yeah, but we didn't like investigate that aspect.
When you were talking about defects, there was a separation going on in the.
Yeah.
Yeah. Is that stable?
Let me see. You mean this one?
You had.
So I think
You had a line graphs on a slide with different colors, and then right when you were talking about this actually. But
oh, you mean the graph for this one?
yeah.
With the eigenvalues, right?
Yeah.
Here, this one. You mean this one?
Yeah,
So this is the same, the simulation I showed you, that's the eigenvector, and here's the eigenvalue.
yeah.
Yeah, so it's stable in the sense that it splits into these two defects, but I think it could possibly be that they move in a different direction if you change something slightly.
But you would expect splitting in more or less.
I think it was more or less stable that you get this split up from this one defect into two, but I don't think it has to necessarily go in this particular direction. So I think if you change something slightly, maybe it will go in a different direction, the separation.
Also, are free boundary models physically relevant?
Free boundary models. Yeah, I guess in some sense, because you may have like liquid crystal and then you may have like maybe some other fluid, or is that what you mean? Like that kind of,
Yeah.
whatever,
exactly.
maybe two-phase flow. Yeah, or like that you have an isotropic phase and that you have a nematic phase, which is when they are like aligned. And actually that's where the different constants come in. So if you have like very disparate constants, you can see some phase transitions like that it like goes from one phase to the other. But you don't need to, you don't need to like, at least for the simulation, you don't need to think about too much where the boundary is of like it's in the model in some sense. But yeah, it may be interesting to study how they evolve. Yeah. Does that answer your question? I don't.
Are there other questions or comments? Then let's thank Agnieszka again.